on the exam, or the last test, which is going to cover chapters 6 and the part of chapter 7 that we've looked at, first 4 sections. On chapter 6, there's fundamental stuff you've just got to be able to do, and if you can do it, you're probably going to pass with, if you do it all right, you're probably going to pass with a solid C, even if you can't do some of the other stuff. When an A or B, you need to be able to do it all. Okay, so you can expect what? Systems with real and complex eigenvalues. We've not talked about repeated roots, okay, because of time constraints we had to omit that. So I'll say no repeated roots. And no consideration of multiplicity of eigenvalues, since you're not having any repetition of roots. So we're not really talking about complete sets of eigenvalues. Or eigenvectors. Okay, that's pretty much, unfortunately, not going to be addressed. I think most people have the linear algebra background to understand this, and it's something you might need to understand in the future, but something you'll be able to pick up. Okay, so, I'm probably going to confine it to systems of 2 equations and 2 unknowns, since it's more time-consuming to do bigger systems. But I will probably give you optional problems where there might be 3 equations or more and 3 or more unknowns. If it's more than 3 equations and 3 unknowns, and even if it's 3 equations and 3 unknowns, there'll probably be a fair number of zeros in the matrix, okay? Now, we have the homogeneous and non-homogeneous case. And people ask a little bit about that, how do you do the non-homogeneous? Well, that's variation of parameters, and I'll talk about that here, so we'll get to that in a minute. Homogeneous case is very straightforward. You just look at the A minus lambda I matrix. You find the eigenvalues lambda, you plug back into the A minus lambda I matrix, and find the eigenvalues. Okay, well, yeah. You know the process. People are okay with this process, I think. Well, okay, we got the non-homogeneous case here. Well, here's what you do for the non-homogeneous case. Here's the theory of it. Here's the result. Actually, no, we need to talk about the psi matrix first because we use it here. So if you have a system, y prime equals ay, then y satisfies the system if and only if it's a linear combination of your solution set, okay? Psi is the matrix whose columns are your solution set. So that, as it turns out, and it's pretty easy to understand why, the psi matrix itself then, consisting of columns that are, that represent your solution set, has to be a solution to the equation itself. So psi prime equals a psi. That's kind of an important thing to understand. And it's really easy to verify. You solve the system, you get your psi, you get your solution set, you put that into your psi matrix, and then you take the derivative of the psi matrix and you multiply the psi matrix by your A matrix, and you find that both sides simplify to the same thing. Okay? And this will be the case provided A has a full set of eigenvectors and the psi matrix is your matrix of a fundamental set. And you don't really have to, there are conditions on this. You have to have a solution set among other things. Okay. Now, so we know what the psi matrix is. So if we have the equation y prime equals ay plus g of t, we find the psi matrix. Now the psi matrix is the matrix of solutions of the homogeneous equation. I didn't write that down because presumably you're familiar with this. If you've done anything with this process. Now, if you know the psi matrix, then all you got to do is invert it and multiply it by your g of t, and you have a u prime. Well, what's u prime? Well, first of all, u prime is something you got to integrate to find the u vector. U prime is a vector. G of t, the arrow over that one, is a column vector. U prime is a matching column vector. So that the first component of u prime is going to equal g of t, so you got to integrate the first component of g of t. So you got to integrate the first component of g of t. Same with the second component, and ultimately then you integrate your not your g of t matrix, but your psi inverse g of t matrix. Okay, and then that's going to be a column vector, and you should know that. And that's going to give you then, when you integrate the u prime vector, it's going to give you the u vector that has the property that psi u is a solution. Now, I didn't write down that, but I'll write it down now. Okay, u is a vector such that psi u is a solution. Now, if psi u is a solution, that means we can plug psi u into this equation, and that's very straightforward. Psi prime, if we plug in psi u instead of psi, is psi u prime. A psi becomes a psi u, and then we have our g of t here, which isn't so far affected. Now, if we take the derivative of psi u, we get psi prime u plus psi u prime. On the right-hand side, nothing changes from this step. Then we use the fact that psi prime equals a psi. Well, if psi prime equals a psi, then psi prime u is going to have to equal a psi u. So psi prime u is equal to a psi u. So these things cancel out of the equation, and we just end up with psi u prime equals g of t. And in the most straightforward way, u prime is going to be psi inverse g of t. Now, if you have a psi matrix, that means you had a full solution set, and its Wronskian was non-zero, and the psi matrix is the matrix of your solution vectors, the vectors in your solution set. So it's invertible, because the Wronskian is non-zero. The Wronskian is equivalent to the determinant of your psi matrix. Okay. You don't have a full set of solution vectors if you don't have a non-zero Wronskian, which means that you have a non-zero determinant, which means that psi is invertible. They don't have to know all that theory to use this, but if you're reasonably adept and have a little bit of time to think about it, you never really have to memorize this. You can always rederive it from the premise that the psi matrix is a solution, which it is, something you should know very fundamentally. And then you just let psi u be a solution, and you're solving for the u vector. And all the steps are reasonably straightforward. Okay, well anyhow, there's your method for solving the non-homogeneous equation. Of course, getting a solution depends on the g of t, on the psi inverse g of t function being something you can integrate. And that can often be a challenge. There are plenty of ways to do g of t functions that you're never going to be able to find the integral of. Okay, so that's the core of what you need to know. Now we go a little further than that. We go into diagonalization, exponentials, and matrices, and so forth. So I'll talk about that a little bit.